Swayam Prabha. Digital India. Educated India.
So all these planes are the same family, which are all called family of planes. Okay, but if you fix one of them as origin, then this particular one will be, okay, you are going to be here as origin, okay, and that one will be 1 unit negative, okay, and you are going here 1 unit positive, and here this is x, this is y, okay. So in the x direction, y direction alone, you have come in the reverse, correct? Right now, you see here, this is y, 1 unit in y. Suppose if I keep this origin here, okay, where you are in y, you are coming back to this point. You are coming in the reverse. So what will happen is, if I have this plane 1, 1, 1, the other one may be 1, 1 bar 1. That 1 bar means going in the reverse direction. Okay, or you can have 1 bar, 1 bar, 1 bar, that is all the three in the reverse direction. Okay, but in other words, instead of complicating like this, you can simply think this as something which when you rotate, you get this or this or this. Very simple. All these planes belong to the same family. Okay, that 1 bar we used to denote go in the negative direction, reverse. Okay, now let's look at this fellow. So this plane which I have drawn here, which includes this lithium atom, that plane is going to be now called, if I accept this cubic as my unit cell, but it is not, okay, I accept that as my unit cell, then this particular plane here will be called as a 2, 2, 2 plane, correct? And this particular plane where oxide ions are present will be called as a 1, 1, 1 plane. Okay, now what you see a lithium, oxygen, cobalt, oxygen, lithium, oxygen. So you have the layer of lithium, oxygen, cobalt, oxygen, lithium, oxygen, cobalt, oxygen, like that. Lithium and oxygen are not, lithium and cobalt are not mixing here. Why they are not mixing? Because they are widely different in their charge. Okay, if I put 1 cobalt in the lithium layer, you have to knock 3 lithium, because there is CO3 plus, this is La plus. It's very difficult. How much material, you cannot move that much material. And also the ionic radii very different. So therefore you will see lithium segregating in one layer, cobalt segregating in one layer, again lithium, then cobalt. Between these two cations, to avoid the electrostatic repulsion, you will put the anions, oxide. So you have lithium, oxide, cobalt, oxide, lithium. So this is a 2D structure. 2D structure. That means if I wanted to remove this lithium, I can come along this plane and remove lithium in and out. Okay, in lithium ion battery, I have to actually move the lithium. So I will move along this direction, in and out. Clear? Cobalt is difficult to move because cobalt 3 plus is not easy to move, high charge density. Now you can see here, we have 2 octahedra, polyhedra, which are edge shared. You also have an octahedra here which is centered over here, because that's also edge center. So if you want between these octahedras, what you have? It's a tetrahedra. Correct, no? How? You can see here, this is an octahedra, this is an octahedra, this is an edge sharing between them, and look at this portion, remove this and fit it here, it will fit exactly here. Correct, no? Because your tetrahedra sharing the face with the octahedra. So it will share a face here, it will share a face here. So this will fit there. Similarly, this face will be shared by this, and this will be available here for further sharing with the octahedra. Right? So that means if you want to go from one octahedra to another octahedra void, that lithium, in this case lithium is in the void, that lithium has to move through a tetrahedra. Correct, no? Why? Because between the two octahedras what you have is a tetrahedra. So the lithium will move to another octahedra, migrate through the tetrahedra. How will you enter through the tetrahedra? To enter through the tetrahedra, it has to enter through this triangular window. This is the triangular window, correct? This triangle, this lithium has to go through the triangular window and again enter this triangular window and get in there. The two triangular windows.
But that also will be in a void.
Hmm?
But that also will be in a void.
Yes. But if ion has to move, there should be empty space. If everything totally packed, difficult to move also. Fortunately, in LiCO2, we don't have anything in tetrahedral void. We have lithium and cobalt present only in the octahedral void. So tetrahedral void is empty. Therefore, lithium takes that route from octahedra to tetrahedra to octahedra, right? Now we can also look at it very differently. It's the same structure. What I have done, I have made a green slab and black slab. What is interesting here? Lithium is highly electropositive compared to oxygen. That means between lithium and oxygen, what kind of bonding possible? Mostly ionic bond. Okay. Cobalt and this. You know, cobalt is a transition metal. Lithium, alkali metal in the left side in the periodic table. Oxygen, the right side in the periodic table. Transition metal in the middle. That means this guy has extreme electronegativity. This guy has extreme electropositivity. This guy has something in between. So this guy can form bond with oxygen. It is neither a pure ionic nor a pure covalent. So this cobalt with oxygen or transition metal with oxygen can form a bond which is not fully covalent, but it has some covalent character. Okay. So whenever you have a covalent character, that means orbitals are overlapping. So there is a band that is forming. So through that band, electron can move. Because when you are doing this battery charging, discharging, you have to pump the electron. So electron has to move in the material. For that, there should be a path. It has to flow through the overlapped orbitals. That's how it will go through that. That's a path for the electron. So this slab will be the electron conducting slab. OTMO means oxygen, transition metal, oxygen. Okay. This slab is the lithium conduction. So that means part of the metal act like a ion conductor, part of the metal act like a electron conductor, both in one material. Okay. So that is why this metal is very good for lithium ion battery application. It's a lithium cobalt oxide. Okay. Now I have redrawn this structure. What I have redrawn, you see here, this is that for A layer. Okay. Or we can go differently. Let's start from here. Okay. What lattice is this? This green one? Triangular lattice. It's not hexagonal. Any three atoms you connect, you get a triangle, correct? It's triangular lattice. Remember FCC, when we discussed, we started with the triangular lattice. A, B, C. Now, look at this green one. This is having atom here, atom here, atom here. So this is not having atom exactly where this is having atom. If this is A layer, then this will be my B layer. Look at this fellow. This is a triangle facing inward. This is a triangle facing outward. So they are not in the same position. So this and this and this are three distinct layer, triangular layer. This again is same as this. Exactly the same position you have atom. So A, B, C, A, B, C. Okay? Clear? So what I have done, I have shown you the triangular lattice stacked one over the other. Okay? Interesting thing is, we go to the sodium chloride structure, we had atoms in the corners and the center, face center. Which atoms? Chloride ions. And sodium ions were in the edge center and body center. but we can also draw differently. Have the sodium ion in the corners and face center. Put the chloride ions in the body center and edge center. Calculate there also it will be 4 sodium, 4 chloride. So we can either way we can represent. You can make a lattice out of chloride or you can make lattice out of sodium. Same lattice. In the void you can exchange the atoms, either sodium or chloride. Similarly here also lithium and cobalt is there. So lithium and cobalt also will now form only the triangular lattice. Correct, no? So now you can see I started with the cobalt forming a triangular lattice, then oxide, then oxide. The red one here is lithium, okay, and again oxide, cobalt. You see this cobalt and this cobalt are not the same. Oxide, lithium, this lithium and lithium not same. Oxide, cobalt, this cobalt and this cobalt not same. This cobalt and this cobalt are same. Correct? Position wise they are same. So what I have done, basically I have given you here and the interpenetrated structure of your anion and cation in triangular lattice with a FCC packing. With a FCC packing. That is what I have drawn. Now if you look at carefully, I told you this has got a rhombus unit cell. Look at this portion. Go from here to here to here to here. What is the shape you get? How many such rhombus possible? 3. So 3 portion, identical portion you put together, you get this hexagonal structure, correct? So 1/3 of that is enough to represent the, it's like a sample, to represent the whole structure. Therefore, even though the lattice is a triangular lattice, just like rock salt, but the unit cell now going to be rhombus, because only that will give me the formula unit LiCO02. How? Let's do that. Do this calculation. What happened here? Something hiding here. So now you calculate how many cobalt are there. Cobalt is here. Okay, cobalt. I will start with the C layer first. C, then comes A, B, C, then A, B, C. That is my anion lattice. Between the two anion, I have to put cation. I start with cobalt. Cobalt, next lithium, okay, lithium. What happened? It's a full screen only here. Okay, you see that? But please note, the cobalt here is between C and A. So I go until my next cobalt is between C and A. That means 1 unit length. Correct, no? So I start with the cobalt, end with the cobalt, which is happening between C and A. You can also start with the lithium, end with the lithium, which is happening between A and B. It doesn't change. Length scale is the same. Okay, so that's going to be unit cell length in 1 dimension. Okay, and that is this dimension. I start with the cobalt. This was a C layer here, and this was my A layer, which is here, and this is a B layer, which is here, C layer, which is here, A layer, which is here. Okay, it goes on like that. Now let's calculate. Let's start with the cobalt. This cobalt here is at the junction of 2 unit cell. So what is the contribution of all these atoms to this unit cell? Hmm?
2 and 3 also.
Hmm?
2 unit cell and 3 unit cell. Each of the
Unit cell will be going like that, right? So it is a junction of 2 unit cell. Also, it is a junction of other unit cell in the sides. First, let us look at it is at the junction of 2 unit cell. Then what will be the contribution? Also, each atom is shared by 3 atoms, nearby atoms, 3 nearby atoms. Then what is the contribution of each atom to this 1/3? There is a 1/3 because one goes this way, one goes this way, one comes this way, 1/3. And again there is a 1/2 because that atom also at the interface of 2 unit cell. So the contribution of each of those 6 is 1/6. Correct, no? The layer itself 1/3, between the unit cell 1/2, so totally 1/6. So 1/6 of the 6 is 1. So all these fellows together will contribute 1. The guy in the center is at the interface of 2 unit cell. So he will contribute directly half. So this guy here and this guy here will contribute half and half. So total that becomes 1. Half and half. Where is it? 1/2 here, 1/2 here. These 2 half will become 1. That is this guy. Okay? And the one in the periphery are these guys. Again 6 into 1 6. This 6 into 1 6 comes from this guy. So there are 2 6 into 1 6. And there are 2 1/2. And these guys are within the unit cell. So they are wholly belong to that unit cell. So 3 plus 3, 6. So 6, 3 plus 3, this becomes 1, this becomes together 1, this becomes 1, totally it becomes 9. Yeah? 9. Similar way you do it for oxide. Oxide we start here, 3 wholly belong to that. These 3 fellows, this fellow wholly belong to that, but these guys are 1/3, and then these 3 belong to that. Again the same trick here, again these 3 here. Then you calculate 18. Lithium you do, you will calculate 19. So I got a formula of Li9 CO9 O18 divided by 9 LiCO2. Okay? But LiCO2 I cannot separate. If I have to get LiCO2, I have to take this rhombus, divide that by 3. Then only I will get LiCO2. Right? So if I take this rhombus, that will have 1/3 of this content. That will be Li3 CO3 O6. So Li3 CO3 O6 will be that rhombus, and that has the same framework as rock salt, interestingly. But in order to meet that rule, that formula unit should match, I have to reconnect the atoms such that a new shape emerge, and that shape happens to be a rhombus. So it's a rhombus.
We can't split the rhombus into one triangle.
1/3 of rhombus you split, you will not get the distribution correctly.
Half is one triangle lattice.
No, you try to split. This guy, no. You split half. You will be either cobalt rich or lithium rich. You will not get, okay? And you want whole number. Okay? Clear? And the crystallographers use this kind of notation where 3, 6 and all means how many times it appears. I told you when you use a rhombus as your unit cell, rhombohedral, then you have to divide this by 3. So Li3 CO3 O6. So Li3, that Li will be 3 Li here, which will be in the site called A site. CO3, there will be 3 CO, that will be the site called B site. And there are 6 oxygen, that will be in the site called C site. So ABC just a house number. And the number, actual numerals 3, 6, 3 and all referral how many lithium and cobalt are present in the unit cell. Okay? By looking at it, I can understand easily there are 3 formula units of LiCO2 in 1 unit cell. Okay. Now we will come to the battery. I have this material. This is a cobalt layer, and say this is lithium layer, cobalt layer, lithium layer. These black ones are oxide layer. Okay. Now this is my cathode material. I have an anode material which is a graphite. Now I am going to charge the battery, and I am charging. What I am going to do, I am going to pull the lithium from here and put that lithium here. This process of pushing the lithium between the graphene is called intercalation. So I am intercalating lithium here by deintercalating lithium here. Okay, if I take the lithium out of a void, I call it as a deintercalation. If I put the lithium into some void, I call it as an intercalation. So there is a simultaneous deintercalation from the cathode and the intercalation in the graphite anode. So that's how your lithium ion battery work. So when I do this process, I call it as a charging. What do you mean by charging? At home you have this overhead tank, right? And you have a sump here with water. How will you charge the overhead tank? Will it charge on its own? It will not charge on its own. You have to use a pump which will charge the material there. So that pump will use the electrical energy which will pump the water uphill. Okay, so your work is done by you. Okay, so now the water has gone here. The potential energy of this water is higher than this water. Therefore, at kitchen, when you are opening the tap, what will happen? Water comes automatically. Why? At the point you are drawing water, the potential energy is lower than the point where water is present, and hence water will automatically run down. So this process of charging the water is called what? Charging in battery. This process of automatic water discharge is called discharging in battery. If you wanted to tell in the terms of electrochemist, this process is called electrolytic. In electrolytic, you have to use electrical energy to do the work. And this process is called galvanic. Here you will get the electrical energy from the chemical energy stored. Okay. So we can call it as a charging, discharging, or you can call that process as electrolytic, galvanic. So every day when you are using your cell phone, you are sometimes using it as an electrolytic cell, sometimes using it as a galvanic cell. While charging is electrolytic cell. Okay. In thermodynamics terms, this is a work done on the system. This is work done by the system. Okay. Work done on the system, work done by the system. Okay. These are all the ways you relate and study. And then now again we look at this visual. I am going to charge the battery. Lithium is extracted from here, gets intercalated here. Now what happens actually? This is my lithium cobalt oxide. M stands for here cobalt, for example. Now when I am trying to remove a lithium, I am removing some lithium N. N lithium I am removing. N is a fraction here. I am removing a lithium N. When N lithium comes out, is a fraction. N is less than 1. You will have N electron is coming out. How can you have a fraction electron? Can you split an electron? Huh? It's a mole concept, right? When I say 0.5 electron, it means 0.5 moles of electron. Graphite made of carbon. This entire thing is a carbon in allotropic form called graphite. Separator. Separator is some non-conducting material which is porous, allows ions to move.
What is the second cell for? There, on the circuit there is another cell.
Where is the cell? There is only one cell.
No, in the circuit.
What did he do here to put the water from here to here? So you need to use some electrical energy, right? So that's a pump. Instead of pump, we are using cell here because here we are not flowing water. Here we are flowing electron. For that you need only power source.
lithium 1 minus m, m onto n na 1 minus n.
So what happens? So you have lithium, cobalt, oxide. I am going to remove lithium from this guy. N lithium, cobalt oxide, N lithium plus N electron. Lithium came from the structure. Where does this electron come from? Because lithium is already Li plus. Where does the electron come from? Oxygen or who else is there? Battery. Where does the electron come from? Cobalt, right? This is the cobalt and this is oxygen. When you remove lithium out, electron either can come from this or come from this. If electron coming from the cobalt, the way I have to write, if N lithium gets out, N cobalt will go to the 4 plus state, remaining 1 minus N cobalt will remain at 3 plus state, O2. Correct? So you add these two, it becomes 1 cobalt because N is a fraction. Correct? So now you see, we have taken this lithium and electron out and we deposit into the graphite and we get a lithiated graphite. You can lithiate up to 1 lithium for 6 carbon. So LiC6 you can make it comfortably. LiC6. Okay? Clear? Any question? Now let's look at in the discussion we had a metal ion which is sitting in the octahedral void. That means that metal ion is in the octahedral crystal field. Correct? So especially for transition metal, the 3d orbital in octahedral crystal field will split into T2G, Eg. Now let us look at cobalt 3 plus. It's a D6 ion. It will be distributing itself as T2G6 Eg0. Why? Because oxide, what is the ligand here? Ligand here is oxide. In the spectrochemical series, oxide is not a strong field ligand. It's a weak field ligand, correct? What are strong field ligands? What are the strong field ligands you know? Cyanide. Then, that's all. Ammonia, carbon monoxide. Okay, so you have a spectrochemical series. That is just a suggestion. If the situation changes, a weak guy also can become strong guy. How? Imagine for argument's sake, not going to do that. I am going to have a gun in my hand, going to pointing, but my hand is shaking. Still, I have a good probability of pumping bullet on him. Correct or not? Right? Now I am aiming someone far from me. Okay? Now the probability decreases. Why? A small deviation in the angle can make my bullet go somewhere. Imagine the last person, your teacher, sorry. Right? Correct? No? Imagine the very last person. Very less probability. Correct? Yes or no? Same here. The weak field ligand can be a strong field ligand if it is sufficiently closer to the cation. Correct? So cobalt 3 plus, it's a hypervalent cation. Okay? So as you go in the periodic table from left to right, you are adding more and more nuclear charge, but your shell is not increasing. As a result, the dominance of the nucleus will be felt, your radius shrink. As a result, cobalt unusually has a smaller size. Cobalt 3 plus more so because 3 electron it has lost. As a result, the oxide ion will come closer to the cobalt 3 plus, and it is sufficiently closer that it itself is enough to split that T2GEG very wide. So you can say now oxide is like a strong field ligand, given the circumstances that cobalt 3 plus is a very small ion. As a result, oxide was able to come closer. Because splitting is so high, the pairing energy is small compared to the splitting energy. As a result, electrons tries to pair up now. Hence, you have T2G6, Eg0. So it is a low spin complex or low spin ion. So it has a crystal field stabilization energy in octahedral field as minus 2.4 delta 0. And if I convert in delta 0 is for the octahedral field. So I can equivalent in tetrahedral field I can put it, which is about minus 0.27 delta 0. The difference between these two is the octahedral crystal stability, octahedral stability energy, what do you call, OSSC. Octahedral, what do you call that? It's this OSSC, I forgot the expansion. This tells you, this value tells you what is the probability of the ion preferring the octahedral voids over tetrahedral voids. So it's a octahedral site specific energy. It is octahedral site specific energy. It likes that to be in that state. So now if you look at the difference between these two guys and these two guys and these two guys, who will have the more OSSE? Cobalt. Okay. So if you have a crystal structure, oxides for example, where you are having cobalt 3 plus, will it go to octahedra or will it go to tetrahedra? You go to octahedra because the difference in energy, if you look at it, it is more favorable for octahedra. The octahedra site specific energy is better compared to tetrahedra. Therefore, cobalt will try to be in the octahedral voids. Look at Na3 plus fellow. The difference is significant, but it reduced. Look at the Mn3 plus guy. The difference is shrunk, right? It's really about only 0.4. So what is the problem? If it is very close, even a slight application of heat can promote the ion from octahedra to tetrahedra, vice versa. That means if you have such a material where ion doesn't know where to go, then you will produce a crystal with a lot of defect. Why? Because ion comes and suddenly it thinks I will go to octahedra, it will go octahedra. Suddenly it thinks I will go to tetrahedra, it will go to tetrahedra. There is no defined rule there. So it will have a mixture of sites, tetrahedra and octahedra occupied by this Mn3 plus, right? No? Whereas this guy is determined, you will go only to octahedra. Clear? Now, look at this. This we call it as a density of states diagram. If you are having allied physics, you might be studying this. So this is the density of states versus energy diagram. Simple terms, the molecular orbital of oxygen we have seen. Each energy level we have seen there. That is same here, energy level. But when you are going for a solid state material, you are not dealing with one atom or two atoms, you are dealing with the n number of atoms. So instead of a molecular orbital, you will have a band. So that's a band here. Okay, band you have a continuum in that. So now you can see oxide 2p band is here. Cobalt T2G band is here. Why I highlighted cobalt T2G band? Because cobalt T2G band is the one which has electron. Eg doesn't have electron. And look at nickel. Nickel Eg has got the electron. Right? T2G is full, but Eg is higher energy than T2G, so Eg lies above the T2G. Okay? Look at Mn. Mn has Eg1, T2G3. Look at here. This is Eg here, T2G is here. Okay? Now, as we wrote, if I am trying to pull the lithium out, every time one lithium comes out, one electron has to come with the lithium. Where the electron coming from? From the transition metal. So in this case, it will come from this band. In this case, it will come from this band because that is the highest energy. In this case, it will come from this band, it's the highest energy. Okay? And energy goes like this. Your vacuum level is here, or your So, as you are coming from manganese to nickel to cobalt, where lithium is more electropositive. Lithium is more electropositive. Where will be its energy? It will be here. Because easy to take the electron out. That's why it will be here. So from lithium to this tells you, that gap tells you what is the voltage of the battery. Then what is the voltage? Which is the highest? Cobalt or nickel or manganese? Cobalt. So if you make battery out of lithium cobalt oxide versus lithium nickel oxide versus lithium MnO2, LiCO2, LiNiO2, LiCOO2, which will give you highest voltage? Which will give you highest voltage?
Nickel cobalt.
How nickel? Cobalt will give you highest voltage because cobalt has got the deep lying d orbital compared to these guys. As a result, you have to promote electron from here to the graphite or lithium, and when you are releasing the energy, that means when you are discharging, it will flow from here to here, so energy will be more. So the voltage of the lithium cobalt oxide battery is more than the lithium nickel oxide than lithium MnO2. Clear? But it is not always true, because again I told you this energy level depends on the ligand around it. Not only ligand around it, also the cations around it. Imagine you have a two polyhedra which shares face, which shares edge, which shares corner. Imagine these two polyhedras which are in sharing contains cations within themselves. Okay, I have two octahedra, inside two cations are there. Now they are face sharing, now they are edge sharing, now they are corner sharing. In which you think the cation to cation distance is maximum? Corner sharing, correct? So that means if I can generate a material where cation to cation is in a corner sharing, that material will be most stabilized material. That means if I imagine I have a manganese, I am making a manganese oxide, I am going to make a manganese oxide in two different frameworks. In one framework, manganese and lithium are in the octahedra, and that octahedra is sharing the edge. Imagine another structure where manganese and lithium, or manganese is present in octahedra, lithium present in tetrahedra, and the tetrahedra and octahedra are sharing the corner. In which it will be more stabilized? Corner sharing. That means if I can make a material lithium manganese oxide such that lithium and manganese are in two polyhedras which are edge shared versus lithium and manganese are in a polyhedra which are corner shared, the corner shared one is preferred. You can ask me, why are you telling me, how is it possible? It is possible. There is a structure called spinel. Have you heard of spinel? Maybe in the second year. Spinel structure, interestingly, has the same anion framework as FCC. What is FCC? You had atoms in the corners and face centers. Correct, no? You had atoms in the corners and face center. Oxidions or anions. And your cations were in the body center and edge center. Right? That is called Rock-salt structure. Imagine I have a structure AB2O4 wherein there are 4 oxygen. That means I will have a 4 octahedral voids and I will have 8 tetrahedral voids, correct? Because my framework of oxygen is FCC. So I have 4 octahedral voids and 8 tetrahedral voids. Imagine the A goes to tetrahedral void, B goes to octahedral void. Then what will be the occupancy in the octahedral void? Occupancy percentage? 50%. What about occupancy in the tetrahedral void? 12.5. 1/8. 12.5. Correct? Now you see there are two materials LiMnO2, another is LiMn2O4. You can assume instead of nickel, Mn2 you can assume because this is 0.5, that 0.5 I add here, I make it LiMn2. Okay. So these two has the same Mn as a redox center. What is redox center? What is redox center? Which accept donates electron. When you are doing lithium ion battery charging, discharging, who is shuttling the electron? It's a cobalt in LiSO2. In LiMnO2, it's Mn. So here, imagine this nickel not there, it is added to Mn and made Mn2. LiMn2O4, LiMnO2. There are two different oxide material. But these two oxide material has got the same anion framework, FCC. But the way they distributed their cation is different. In LiMnO2, both the cation in octahedral field. In this, lithium is in tetrahedra, Mn is in octahedra. Occupancy is not full. Okay. Now you see this is a battery voltage. In LiMnO2 battery voltage is 3.5, whereas in LiMn2O4 battery voltage is 4.5. Where is this change coming from? Remember I told you, the polyhedra sharing makes so much difference in voltage. Can you believe? That's why I told you structure, bonding and electrochemistry. Electrochemistry, even though it's the same manganese and the same manganese in the same octahedral crystal field, but voltage is different. Simply because the repulsion between the lithium plus and the Mn3 plus is manipulated depending upon where lithium and manganese occupy in the structure. Correct, no? So that gives you can ask me, why are you excited with high voltage? What is energy in a battery? Energy is voltage times capacity. Voltage times capacity is the energy. What is capacity? How much lithium I can hold or how much electron I can hold. That's called capacity. So coulombs into voltage, it tells you the energy. Correct? No, electron volt. E has a unit of coulombs. Volt. So electron volt is a unit of energy, right? So if you wanted to store more energy without changing capacity, what you should do? Increase the voltage. If you are in an apartment, and if you are in a ground floor, open the tap, water will come like anything. If you are in the top floor, you have to turn few times to get some water. It's the same capacity tank, but one guy gets the energy at high speed, water at high speed. One guy gets at low speed. What's the difference? The one in the top floor is close to the tank. So the point where he opens the tap to the top of the tank or the level of water in the tank is the potential energy difference. And that is the energy with which water is coming out. That's energy discharged due to water delivery. Correct? But the same water, when it comes all the way down, it's accelerated by gravity. So the potential energy difference is huge. So even before you open, water flashes. Correct? No? Yes or no? So how will you do that? How will you do this, solve this problem? Very simple. Because I don't like to go to this, Kalyana Mandapas. Because the mandapa will look very nice. When you finally go to wash your hands, they will make it like a public toilet, They will have a stainless steel wash basin, very long one with a lot of taps. You open the tap, that water hit the bottom and splash on you. Why can't they adjust the speed? Such that water comes at normal speed, nobody bothers, right? That's why every time, because of marriage, I am going with very well dressed. I don't want anything spill on me. So always I go like this and do like this, right? Correct, no? By simple physics, you can manipulate it. How will you manipulate? How will you manipulate that? You can give a U-bend, slow down. Okay, the depth of U-bend can be different for a different floor. So that finally you get it. It's a very simple calculation. We don't need to do anything, but our people just not change certain things. They will do, this is how we will give you. It's not the way. Anything we do, there should be a perfection. Otherwise, it's really boring. You understand? No. Now it's time. Another 5-10 minutes, I will close. So you see, same manganese, same octahedral crystal field. Just because cation distribution in terms of the voids is very different, you get the different voltage. Now let's see LiCO2, LiMn2 both same anion framework. What is anion framework? FCC. This is LiCO2. This you have seen. Now you can see here. This is octahedral void. In case of LiCO2, this void will be either occupied by lithium or by transition metal. Also in the edge centers, right? And this is the, you can see here, this triangle is the common phase between this tetrahedra, octahedra. Same here. But here I put lithium or transition metal in the octahedral void. Whereas here I put the lithium in the transition metal in the octahedral void. But remember, in LiMn2O4, in this one, what was the occupancy in the octahedral void? What was the occupancy in the octahedral void? LiMn2O4? 50%. That means every alternative octahedral void is empty. Correct? So, this particular octahedral void now will be empty. So, you have lithium here, octahedral void empty, lithium here. And the next octahedra will have the cation inside. Okay? So, I assume it's a chain of octahedra. Every alternative octahedra is empty. With that octahedra is capped by the lithium tetrahedra. So that there is no cation here, so there is no repulsion. Actually, this is a corner where another octahedra is meeting this tetrahedra. So there is a corner sharing between the tetrahedra and the octahedra which is filled. Correct, no? How will you visualize that? Okay, this is a phase sharing, edge sharing, corner sharing. The gap between the cation changes. Correct? Let's do. Now let's look at this. This is a spinel. To understand the spinel, since we have understood the FCC lattice, we will start with the FCC lattice. Remember, for LiCO2, I could not use the same unit cell shape as NaCl. Why? Simply because instead of one cation, I had a two cation and they were segregating. Therefore, I had to choose a shape of rhombus. Then only I could able to reprint. Although framework is same. Now also I am going to do the same thing. I am going to take an FCC unit cell. You see it's an FCC unit cell. This is also an FCC unit cell. In this FCC unit cell, how many tetrahedras are there? Total how many tetrahedras are there? 8. But I have put only in 2 lithium. Okay. In this FCC unit cell, how many tetrahedra are there? 8. But I did not fill. But rather I filled one octahedra here. Okay. Now what I am going to do, I am going to combine this and 4 unit of this, 4 unit of this alternatively. You combine first these two. Combine third one. Okay. This one you put it below here. Then same thing you put it here. You can clearly see all tetrahedras are aligning in one line. And between these two tetrahedra, we will have octahedra and that will be empty. Okay. Now put it 2 behind. So you will get these 2. 2 in the front, you get these 2. So you can see this is in one line, this is line below that, this is line above that. Okay. I will only take this slab, this particular slab. Put it here. Now you can see this is an octahedra yellow region. This is an octahedra yellow region. This white region you see it is also an octahedra. Can you see that? 4 here, 2 above and below. So it's an octahedra. But here cation is there. Here cation is there but no cation here. But I put lithium in the tetrahedra here, lithium in the tetrahedra here. This tetrahedra sharing phase with this octahedra, right? But it is sharing corner with this octahedra. But here there is no cation. Therefore, the distance between this cation to this cation is large now. So it is most stabilized structure. Although Mn is still in the octahedral field, now because structure is stabilized, okay, So the voltage difference is high. So battery gives high voltage. Now how the lithium will move? Lithium will move from this lithium tetrahedra to this empty octahedra to this tetrahedra, then to empty octahedra, then tetrahedra. So this is a path of lithium movement. Okay. Now one more thing, this may not be important for you. We call this as a because remember I took 2 subunit cells, 4 of each. So totally 18. Totally 8. Correct? Remember? How many? 4 of these I took to make this. Each one is an FCC lattice. Correct? Each one is FCC lattice. FCC lattice, how many atoms, anion? How many anions in FCC lattice? 4. I took totally 8 lattice. So 4 into 8? 32. So I will have a 32 atoms forming a big unit cell. Anion O32. Correct, no? If anion is 32, how many octahedral voids will be there? 32 octahedral voids. So octahedral voids, I separate 16 and 16. Why I made it 16 and 16? Because I had this material LiMn2O4, but only 50% of the octahedral voids I can occupy with the Mn. Therefore, this Mn will go to one of the octahedral void, other will be empty. Correct, no? And then we have a tetrahedral void. How many tetrahedral void will be there? 64, correct? But in that, how many lithium I can put? 8 unit, no? 8 lithium only I can put. 1/8 occupancy, no? 8 lithium only I can put. So 8 out of 64 is 1/8 again. Clear? So now you can see here, this 8A means 8 tetrahedral sites. 16D, 16C and 16D. Why 16C and D? They are distinguished because one is filled, one is unfilled. So one is 16C, another is 16D. Okay, but it's not required, but this is how the crystallographers distinguish one octahedra from the other because one is filled, the other is unfilled. Okay, the last one, you can visualize this crystal structure of a spinel. You can see this is a type 2 lattice, that was type 1. Now we are going to merge them. See the type 1, you see 2 lithium tetrahedras are occupied. This is no tetrahedra here, they are coming. And these ones are my manganese. Okay, they attach each other. Now they will rotate. You see all lithium tetrahedras sometimes in a zigzag line. Okay. Now you see this direction, I call it as a 001 direction or 100 direction or 010 direction, which is a Miller indice. What is Miller indice? If I go only 1 unit along X and I go parallelly to the Y, parallelly to the Z, then it is 100 or 010 or 001. I will replay this. You visualize all the 3 directions I said. One is this, another one is this, other one is this. In all the 3 directions you can see lithium. That means in this material I can push the lithium from all the 3 directions, which is very different from LiCOO2 or LiMnO2. There we had lithium in a sheet, a 2D structure. Here I am having lithium in a 3D structure. So that means I can enter the lithium into this material in all the 3 directions, X and Y. Whereas in case of LiMnO2, I can enter the lithium only in X and Y or Y and Z, whatever the direction, right? So what is the problem? Suppose you have a house. To that house, you can enter from any direction, then you will get into the house very quickly. Suppose it has only one door, then what will happen? You have to go around the house, come to the entry point and then enter, correct, no? So your rate of entering the building will be slowed down if you have restricted entry. Similarly, the lithium entry exit is slowed down in case of 2D material compared to 3D material. Why is it important? Because we wanted to buy electric vehicle provided, we will buy electric vehicle provided if the charging takes no time. If someone says buy electric vehicle but charge overnight, I don't want. If I have to go on the highway, 10 minutes like refueling car, I wanted to recharge my battery and go. Correct, no? So therefore, C rate is called C rate. How fast you charge, discharge battery is very important. That depends on the dimensions of the material. Whether it's a 3D diffusion of lithium or 2D diffusion of lithium. That's very important. Therefore, you just watch once again. I will stop with this. See, lithium can enter like this, can enter like this, right? So it's a 3D material. So what we learnt, same redox couple but different voltage, all because of the structure and bonding. Okay? Hopefully, if you have any question, I can answer, otherwise I am done. Any question? No question? Okay. Yeah. Huh?
What is T2G and EG?
T2G, the G stands for gerade. Gerade. Gerade means symmetric. For example, if you, I think you will study the quantum mechanics in the second year. Suppose you have an orbital like this, which has facey phase, and from the center, if you go in either direction, the magnitude of your wave function will be the same with the sign. Okay. Whereas if you take a p orbital, from here you travel this way and this way, the magnitude is same, but the phase is different. So this is ungerade, this is gerade. It's called even orbital, this is called odd orbital. Okay. The T2G is a terminology you will study in your class. G stands for gerade. Why gerade? Because this is a d orbital. D orbital, how it will be? Correct? Correct? So go any direction, same. So it's a gerade. What are those orbital? dxy, yz, zx. Right? What about EG orbital? EG orbitals are dx squared, y squared and dz squared. That also gerade. Okay? But this terminology is given because of the symmetry that is not beyond the scope of this thing. You can assume that these three orbitals are grouped under this name and these two orbitals grouped under this name. The G alone can easily explainable now, that is gerade and ungerade. That means there are even type of wave function. This is an odd type of wave function. Odd wave function, mathematical function, odd function are called ungerade, even function are called gerade. Yeah?
Why the 2, sir, before G?
That's what, those things will take time. You just assume this is a name. Why you have particular name? Nobody can answer, right? So it is whoever coined this, come up with some methodology and coined that way. So that nothing to do with why it is like that. You can change, but if you still know the principle underlying that is fine. But don't worry about that. For now, it is not required. So you just see it's all grouped. It's all, if you study group theory, you will know. But that's again beyond the scope of this class. Yeah.
Knowing group theory, they are learning it in
10,
college.
12, yeah.
Learning in 12, sir.
You will see CFT, crystal field stabilization theory, you will get that.